On the fifth day of our 5 days faculty development program on manufacturing and automation, I welcome all the participants, distinguished speaker, respected principal, Dr. Tikeda sir, all HODs of our college, ladies and gentlemen. Today we have the session on uh, manufacturing from ancient statues to human implant, and that will be delivered by our distinguished speaker, Dr. Vidyut Desar. He is from NIT Agartala. Dr. Day was graduated in year 1996 from NIPT Hatia Ranchi. After graduation, he joined as a territory manager at Hindustan Motors, and uh, after that, he joined academics and got masters and PhDs from IIT Kharagpur. Thereafter, he joined NIT Agartala in the Department of Production Engineering in the year 2012. Dr. Day has guided 3 PhD scholars and many more scholars are registered presently. He has published more than 25 papers in reputed international journals of good impact factors. Beside academics, Dr. Day is actively involved in academic administration. He is Associate Dean, Dean Academic, and in charge of Institute ERP system. With this introduction, I hand over the session to our distinguished speaker, Dr. Vidyut Desar. Sir, please continue. Sir, do you hear us? Sir, do you hear us?
Can you hear me now?
Yeah, yes, sir. We can hear you now, sir.
Okay, thank you.
Thank you.
So, yeah, I'm getting a lot of hiccups before I could start. Anyway, so unlike a daily class, this FDP means like I will be talking to the faculties, and there will be like research scholars as well. So the aim of this talk is not a class work type of thing, but to give you information regarding the topic. Now, what type of informations am I going to give you? Like I will be telling you how our manufacturing, since we all are related to the manufacturing only, how this art of manufacturing was invented, like when people, didn't learn to talk as well. From that time onwards, how manufacturing changed its mode and has become so sophisticated now that we are in a position to manufacture something out of commodity, and those things are being put inside our body. So that is the realm of manufacturing that we have covered over these thousands and thousands of years. So in my talk, what I am going to do is, like, I will be presenting to you what manufacturing is, how it started from prehistoric era, and then it traveled all the way from the like subtractive manufacturing, slowly and slowly, how we have come from subtractive manufacturing to the era of additive manufacturing. And I will be like informing the audience more into how this additive manufacturing is being utilized in the like biomedical and into the human implants. So that is how we are going to see in this small talk. So these are the areas that I will be covering. Now, let me go to the next slide. Next slide shows what? To a layman, it may
Sir,
appear that, yes.
I want to say, sorry to interrupt you, sir. Sir, if any of our participants having any kind of doubt, is they can ask in between or at the last they will.
No, I think you just like note down things and we can have a discussion at last, because like we are having a time constraint also. So let me finish my part, then we can have a discussion as long
Yes,
as
sir.
you want. Okay.
Yes, sir. We will. So
Thank you.
please.
Yeah.
Thanks.
So to a layman, like whatever I have presented here would be like a bunch of stones of different shapes. Yes, truly they are. But all these shapes that I have provided here, put up here, they were very, very significant if we go back few thousands of years back. Now, when like man, like what we call today as Homo sapiens, when from quadruped they tried to convert themselves into biped, like instead of crawling, they started to stand on their two legs. They were able to utilize their other two limbs, which earlier like they used to crawl. Now that those two limbs have become free or become free, and since this Homo sapien was physically weaker compared to the other like animals present, so in order to survive, they tried to utilize the other two limbs. What they found was that they had got intellect far better than the other animals. Now, this intellect that we still have today, and we have this intellect is ever increasing and growing in its arena and span. So, with this intellect, he tried to deceive the animals. He tried to learn to hide himself. Now, hiding oneself into some area is also a characteristics of all animals also. But man, since he is superior to animals, like he tried to utilize this instinct to shoo away animals. He learned that if he throws something at the animal goes away. And if something that is thrown properly, and if that is thrown onto the animal and the material has got some sharp edges, it could injure the animals as well. Now, these some of the things that he kept on noticing that helped him to derive out the tools that we see over here. Now, we have got a long history of how these tools have been shaped, carved, and utilized for their necessity. Not only were these tools that we see here made up of stone, which we can say that these are the first manufactured thing human could have done, but later on, he found that shaping these tools would be very difficult. Shaping a rock would be difficult. So he like switched on to something else. What that could be? Let us see. Now here I have shown you the skeleton of an animal. Now this animal, like it very much looks like a bison of these days, but in the prehistoric time, it was definitely an animal of larger shape and size. Now, the skeletons have been recovered from the area of ancient Greece, and during those days, people used to call themselves as Iowans. And the bones of these animals were used as raw materials for making their tools. Now today we know that bone is what? Bone is a natural composite, God-made composite. And now we are trying to utilize the technology, how bone is formed, such a wonderful composite. Knowingly, unknowingly, whatever be it, man realized during those ages that the bones of these like animals, they can be used for their purpose. So the art of manufacturing had started from that era. So in what way can the bones can be shaped? We have shown two things. One is bone breaking, like they will be taking a bone, place it on another larger like rock and strike it with a smaller rock. so that bone can be broken down into smaller and suitable pieces. They also found that the bone can be ground with help of a sharper like stone. So bone grinding is also a part. So these were the two tricks that were used to shape and size the bones. The first, like we can say, art of manufacturing. Nowadays, we and our students, they study like immensely the manufacturing processes. In manufacturing process, what do they study? They study material removal, machining. So whatever we saw, like that has the roots in these two slides that I have shown you. That is the first one. Let me take a pointer. Yeah. So this one, in bone breaking, this can be thought of as cutting principle that we are having with different mechanisms. And this is bone grinding. It's a material removal process, maybe machining process. And let us go to the next slide. Next slide shows us 4 different types of tools that were used in those days. One is bone hoe, there is bone scoop, bone knife, and fleshers. Now, how were these made? The bone hoe that we see here, these were generally made out of the scapula. Scapula means the bone that is there in the shoulder blade. So the shoulder blades of like bisons and elks used to be modified, and this took the shape of a hoe. These type of hoes are used nowadays also. Definitely they are metallic, with help of which we dig soil. The next thing is what we call as bone knife. Let us take this bone knife. How are these bone knives made? These bone knives are also called as squash knives. Now, these are also used from the scapula. This part of the scapula, if it is broken, it can be treated as bone knife, because the blade of the scapula towards the end of the scapula, it is very sharp, and they used to grind the bone and make it sharper as well, so that it used to be like knife. Next comes bone scoop. This part. These bone scoops, they were made up of what does it resemble like? It resembles like a horn of a cow. Yes, definitely. Maybe the cow that we see in the present form, due to the sake of evolution, the cows were not looking like these they are doing now. But these type of bone scoops were made from the horns of a bison. So bison's horns were used, and these horns were again a little bit shaped. They were made sharp, and they were very good tool in digging mud. So this is the third tool. Next, we have got something called fleshers. These fleshers were used from the foot of the bison, which we call as metatarsals. Long foot bones were used. They were chopped. They were made halved, and when we eat mutton, then we have seen to ourselves also that the long bones, if we can suck out of it, we can suck the bone marrow and it becomes hollow. So similarly, a bone of that bison, if it is cut and it is shaped like this, keeping it for some time, the bone marrow will decompose and dry away, and we are going to get a flesher like this, which will be utilized, or which was utilized later on by the people to rip out flesh. In a similar manner, we can see here, there are different tools which were used. One of the major tools that was used is this fishing hook. Now, how did this hook, or where did this hook come from? This hook came from the hoof of the animals. See, this is the hoof of an animal. The inside portion of the hoof, which contains flesh, decomposed over the time, and they got only the outside hard portion of the hoof. Now, from this hard portion of the hoof, they grounded off the other half portion, so that they were left out with a hook shape like this. This is what is called fish hook, and this fish hook was definitely utilized for fishing purpose. There is also something called a sickle. This is called sickle. The sickle in the is utilized till date in its metallic form. Now you might be wondering where these sickles come from. Now these are again modified jaws of deer. The jaw of a deer could be modified in this manner, and they were used as sickles. Then we have got awls. This awl has got a very pointed end, and this pointed end of this awl was used to stitch. Stitch what? Stitch the hides that they used to wear. Like they weren't getting clothes like we do, but somehow they had learned that they could hold together two pieces of leather together with this awl. Now all these discoveries that were being done is due to the inquisitiveness of human mind, with help of which human being is always wanting to like know more and more, learn new things. He is reacting to the situations. He is keeping track of what he has seen today, and he tries to remember and try to utilize the similar situations when he comes across next time. That 2 days ago, same thing had happened. Today again, it is happening. How did I overcome that? Now, this type of like correlation of things had made man what he is today. Now, let us keep ourselves confined to this manufacturing only. Slowly and slowly, we will be moving into the deeper sense of this manufacturing. Here we have shown that a man took a flat stone, and he somehow realized that the edges of these stones are brittle, so he could use another stone to chip it off. And once he chipped off the edges, he found that the edge becomes very sharp, and this sharp edge could be utilized for many purposes. Then he found that like he is not getting leverage with this tool, so he could use it as a hammer, provided he could add a handle to it. So that is how he could add a wooden handle. If you can add a wooden handle to it, it becomes X. So the part of stone shaped into this manner can be converted into an X, the first like rudimentary X of non-metal. With help of wood, he like developed different methods of tying this wood to this, and that is how he has developed the first wood, first X, stone X. Now, these whatever we have talked till now, these are something that we have seen in the Paleolithic age. That means the entire era of our history can be divided into Stone Age. Stone Age can be further divided into like Old Stone Age, Paleolithic age, and then at the at the end of the Paleolithic age gives us the Neolithic age, where the rudimentary tools which were used in the very crude form during the earlier ages were now being shaped into more better tools, having the capacity to be named into different features or commodities. Now, here comes the end of the Paleolithic age, and then comes the Neolithic age. Let us see what we get in Neolithic age. In Neolithic age, again we see there are like utilizations of stone. Like these are the like pestles where like people by this time they knew how to grind. Like they used to started cultivating, because the end of Paleolithic age again gave us the invention of agriculture. So they started to like grow grains, and the husk of the grain would be too difficult for the human teeth to grind. So they knew that how it can be ground. They took the stone and pestle, they knew how to grind it, and they started making earthen potteries during that time. So these are some of the artifacts from Neolithic age. By this time, they did not know how to utilize the metals. Metals were not invented during that time, but definitely they had invented fire, and with help of fire, they could tame many things, and they utilized this earth and clay to form potteries, and they also knew how to bake them. So this invention was there. Now, after this, that is now, till now, what have they what have they manufactured? They have manufactured something from stone. They shaped them into tools. They also knew how to use earth to make earthen potteries. And they also invented fire, so they can fire those potteries and make them harder and stronger. Now, when they were using these potteries and they were making they were using fire to like harden these potteries, somehow, somewhere, we do not know at the moment, but definitely they have come across the metallic ores, which might have looked like stones initially, but when they were building fire, then some of these stones might have melted and they have flown. See, as we know very well that man is very inquisitiveness. He has got the ability to think and analyze and question why it is happening, how it is happening, when did it happen. Since these questions were there in his mind, so he might have noticed and realized that there are some particular variety of stones which, when subject to heat, it melts. And this molten metal, it again solidifies. And this was the idea which he utilized to what we call as the modern day castings. Now, in this slide, I have shown the first and most rudimentary shape of a metal casting. This is this amount of metal, which might have accidentally melted and solidified into crumb. So this is it. Now, then he started imitating that. Now, since this metal or this material, which when heated melts and again when it solidifies, when it cools, it solidifies and takes a particular shape, then he thought that this is an easy way of generating shapes. Because earlier he had an experience of shaping stones, which was very, very difficult to do and took long time. But here he found a method where he could take a material, he could subject it to fire, which melts it, and when it cools, it solidifies into definite shape. So that is how he started making these shapes that are shown here by the method of what we call today as casting, that he used to melt them and pour them into some shapes, and then once they solidified, they used to get this. So the art of forging came very much later, but initially people learned the art of casting. So the casting again came accidentally. So over like this does not happen in a day or two, maybe thousands and thousands of years they had been doing all this thing. And then only they have learned and mastered all this art. So again, I'll come back to what the little bit about history. So the history can be divided mainly into three ages. It is Stone Age. We have seen the Stone Age could be divided into two, Paleolithic, Neolithic. And then this slide that we are showing, this is the starting of Bronze Age. So Bronze Age casting. Then the Bronze Age will end and it will be coming to the Iron Age, which is still prevailing today. Now, the casting Bronze Age would be giving its way to the wrought ammunition in Bronze Age. That means after utilizing the castings for thousands of years, he learned that the casting that he used to make, that used to break. So it was brittle. Somehow he found that if the castings could be heated time and again and beaten, hitting HEAT, hitting and beating, that is hammering, it becomes very strong. And that is how he learned the art of making swords. See, I have a picture which shows the Bronze Age ammunition, how they used to make the swords out of bronze. They used to be weaker than the iron swords, but well, this is how they used to make. Not only did they learn the art of making swords, but again they utilized metal for their own purposes also, day-to-day purposes. What would be these day-to-day purposes? See, this is the day-to-day purpose. though the quality of the picture is not good, because like this is actually a human figure having a bronze mirror. In those days, they did not have the glass mirrors, no, painted with mercury. Those things were not done. But definitely, they had got metal, and they used to shine the metal to such an extent that one could see one's face. So the mirror used to be like that. It has got tarnished over the edges, but when maybe we are expecting that when it used to be at its peak, the best quality made, it used like a human could see their faces on its reflection. The next thing is what? Bronze cookware. Now, this particular photograph, this is showing us what? Like the man not only knew the or mastered the art of melting metal and putting it into different shapes to get a casting, but apart from that, you see the intricacy of this casting. We can find that on the surface there are so many small minute details that has come up with the casting. So all this artistic work also man had learned by this time. So man now is no more dependent on stones only. He has got the art of melting metal, pouring metal, not only melting and pouring metal, he has also learned the art of hitting the metal and hitting it, HITTING, hitting it. And that is what we call as forging. So slowly and slowly, if we talk in terms of today's terminology, he has learned the casting, he has learned the metallurgy, because now he is not only using what we call as pure copper, but he has learned to make alloys by like adding zinc and tin into it. So that is how this is called the Bronze Age. Now, this has been going for centuries together. Now, these things are like how old? Maybe 3000 BC. Now, so from 3000 BC, these have been recovered from the ruins of Mesopotamia. We can come down to our country, and like the history books that have been written, which we had studied in our school, say that the like civilization or the Indic civilization started from 2000 2500 BC onwards from Mohenjo-daro and Harappa. But lately, the historians are discovering that it's not only like contained to 2500 BC, but it went beyond that, maybe 5000, 6000 BC also. Now, over those years, like our country has also seen marvels in this casting technology. Where do we see this casting technology? In which form? Again, let us see in the next slide. This slide shows us two photographs. One is your Kaliya Daman, that means this is a mythological story that we all know. This mythological story has been converted into a figure. Has been cast. It's a bronze sculpture. Both of them are bronze sculptures. One is the Shiva and other is the Kaliya Daman. These are way back like 2500 BC, and not only was like if man could like cast such a complicated what we call as Shiva statue out of bronze, then you can imagine to what level the castings were available during that time. It has been said that India learned the art of investment casting, which we learn today in our class books, during that time. So these type of like statues were used by the famous lost wax process or investment casting that we call today. By this particular process, we know today that very complicated shapes can be formed. So the Kaliya Daman that we see here, this is from Chola dynasty, that is from Tamil Nadu. And the Shiva family that we see here, this is from, this dates back to 10th century AD. And this has been recovered from some part of Bihar, the erstwhile Bihar. Next, we see two statues. One is of Lord Ganesha, another is of Lord Nataraj. Now, the Ganesha is from Kashmir, 7th century, dates back to 7th century AD, and this is again from the Chola period at around 1100 AD. That means from BC, before Christ or the before Christian era, to this age, like 1100 AD, so after that. How man has progressed from these mere stones to such integrated and complicated shapes. Now, all of these are related to castings only. But as I said, that casting is not the only technology that was developing. Along with casting, there were many other things which were developing, and one of that was forging. That means you heat something, cool it, again heat it, cool it, and when you keep on repeating this, we all know like metallographic changes or metallurgical changes are taking place inside it, and it becomes hard, very hard. So not only was the man dealing with bronze and bronze related material, but he found another important material which is called as iron, which was stronger, which was abundantly available, and he learned to tame iron as well. Next, I'm going to show you something which people today still wonder. What do we see? We see the famous rust-free iron pillar at Delhi. This iron pillar is said that it was manufactured during 400 BC. 400 AD. 400 AD, it was manufactured. Till date, people are wondering that it does not have any rust. It didn't rust till today, and we know, like over the last 20-30 years, how polluted Delhi is. In spite of that, it is not rusting. So people have done lots and lots of research onto this, and they have found that it has got an extraordinary corrosion resistance power. Over 1600 years, it did not face any rusting, though we know that the temperature in Delhi, it soars as high as 45 degrees centigrade, and it is cold as well, very cold, but it is still like sustaining all this what we call as atmospheric atrocities, but still it's not getting rusted. So we Indians, we had developed the metallurgy to that extent that we could develop something which was not getting rusted. Apart from this, this is the most remarkable feature that is in exhibition to all people. But apart from this, there were many such type of artifacts made, which over the historical time has perished, got lost, did not get prominence. But this one is still there. Now, lately people have studied the metallurgy of this type of iron pillar, and they have found that it contains very high phosphorus and absolutely does not contain any sulfur or magnesium. Now, these are typical thing that it has got iron, high quantity iron, definitely is less than iron, and it has got very high phosphorus without any sulfur and magnesium, is thing that is bothering the metallurgists. Metallurgists from IIT Kanpur, they have analyzed, and they say that it contains a compound, this type of pillar, it contains a compound of what we call as misawite, MISAWAWITE, misawite. Let me try to, if I get a pen, I can write here. This is MISAWITE. Misawite. What is this misawite? This is a compound of iron, oxygen, and hydrogen. They call it FOOH. Now, this is the compound which is responsible, as people say, which is like resisting the oxidation of iron till date. Such a wonderful discovery of the date. But I wonder, like people or the metallurgists of 400 AD who had intentionally developed it so that it won't rust, and that is how it was made into a monument and kept. So definitely, it is not that we are learning things. I can also say that we had learned things, we have forgotten them, and we are relearning it at the moment. So that is this. Now, having said all these things, let us now come slowly into the engineering aspect and try to learn things or see things in the present context. So historical things we have seen, many things we have seen. So we have now in the present context, if we talk of manufacturing process, we can say conventional manufacturing process and unconventional manufacturing process. In conventional manufacturing process, what we are having the formative type where we are like melting metal, we are pouring it into the molds of particular shapes and it is taking the shapes, which we popularly call as casting. Next is what we call as the subtractive type of machining. What we do there, like we take initially a larger piece of material, then we find that this is too large, too big for my purpose, then I'll remove material from it uh, by machining, which we popularly call as machining. But the prehistoric man was also doing the same thing, if you remember, like he used to take a big piece of rock, then with help of other rocks, he used to like chop it off and turn it to a shape which would be handy for him. Similar things he used to do for bones as well. That means machining that we are doing today, definitely with help of machine, we are calling it machining. That means we are removing materials from it. The idea was there in his mind during those periods also. Maybe he was not doing it with help of a machine, he was doing it manually, but material removal was there. Next popular process is called the joining process, fabrication process, which we popularly call as welding and soldering processes. We do not find an exact like mention of welding process that we are using today with help of electricity, that is arc welding sort of thing. Those things we are not, we did not get any trace in history, but definitely forged welding was there, which is still taught today in type of pressure welding. If we are teaching our students different types of weldings, in which pressure welding is one, there what we do, we heat something like above the recrystallization temperature, like, and then we try to hammer it and we join the things together. So that is like forging, or we can call it this type of forging are still in practice by the blacksmiths. Now, what are the weaknesses of these processes? The weakness of these processes are that we have mentioned, all these three processes are that these processes are generally carried out for large materials, large size things, and small things are not possible. See, when I'm talking of manufacturing, uh, there can be a two way of thinking. One way is that because of our muscular power, man had always wanted to make big things, huge building, and there would be a competition that if I have made two-storied building, the other will be making three-storied building. Like how like the sizes are increasing. So man, as an engineer, would be wanting to make large things, big things. On the other hand, the same person, the same man would be also interested to make smaller and smaller and smallest thing. But the processes that we have discussed, the traditional casting process and the machining process and joining process, they have got some limitations with help of, due to which you or I cannot make very, very small things. But if we are into the present requirement of biomedical engineering, there we find that very intricate shapes are required to be made, manufactured. But there is a limitation in the manufacturing process, and we are unable to utilize those manufacturing processes to suit our needs. So that is how man had always been looking for an alternative with help of which one can manufacture those things. Now, here we are from 1980s onward, we are developing another type of manufacturing which we call as additive manufacturing. All the manufacturing that we had learned earlier were the conventional manufacturing which were mainly subtractive. But now we have learned to make additive manufacturing. Additive manufacturing means what? Like we will be starting from scratch. So starting from scratch means starting from dust, starting from powder, and slowly we will be joining these powders together to make something big. So we are in the manufacturing, we are going all the way around. We are starting from material, we are melting it, and we are making big things. That is one way out. Next thing is that we have a big thing, we are like removing material, making it small thing. And then there is another way of thinking where we are starting from powders and then we are converting into like larger things. That is what is called additive manufacturing. Now, in this additive manufacturing, we will be developing these 3D structures layer by layer. That means when we keep on adding one layer after another, slowly and slowly, a large thing will be built up. Now, how are these things done? How are these additive manufacturing done? Well, there are different methods. These additive manufacturings can be done for metallic materials and for non-metallic materials. So we will be keeping our discussions confined with most of the non-metallic materials, because we all know that non-metallic materials are easy to melt. Because in this process, additive manufacturing, definitely melting would be there. Not the way the metal is melted for casting, but definitely melting would be there, but in a more controlled manner. So we are going to see that. And there would be techniques where we will not be melting the material in totality, but we will be doing something so that the powder that we have taken as an initial material are held together into one piece. So let us see how this can be done. Here we are having the example of what we call as powder-based printing. Powder-based printing. What we are doing here, this method is called a jet binder jetting. Also, this is called. Here we are having two chambers. In one chamber, this chamber, we are storing the powder. All right. And from this chamber, the powder will be dropping into the next chamber. Both of them have got two pistons. We have got a roller also here. So what will be happening? These like powder feeder, this like piston is going to move up slightly. As it moves up slightly, simultaneously the roller is going to move over it, and it is going to scrape out the excess of material that is coming out, and it is going to dump into this like container. This container has also got a piston which can move up and down. So the material, the powder material falls there. Now, what does this, what we do with this material now? Now, what we will be doing on the powder which drops here, we are assuming here that the powder, once it is dropped here, it is uniformly spread. Since this is a schematic diagram, we have not been able to show it that way, but it is assumed that once the powder drops here, it spreads out uniformly. Now, once it spreads out uniformly, then there will be a head on top of it, which we are trying to compare with the print head. Now, from there, like the what we call as a glue will be dropping from this particular head onto this surface. Glue. So this glue will be falling on these particles, not all over, but at some select places in a particular orientation. And on top of that glue, we will be adding more powder, and then again glue, more powder, again glue. and at regular positions only. Like I want the glue to fall here, not over here and here. It will be falling here only. So once it falls here, once it falls, it falls here, not here. And if it keeps on adding, so what will happen? The height is going to increase. Once the height increases, like I give some powder and then this drops onto this, allow it for some time to settle, it solidifies. And then what I will do, I will pull this down. So as I pull this down, there is an opportunity to pour more powder. So more powder will be poured here on top of it. Again, glue comes, it sticks to the earlier one. And then again, once it solidifies, it is pulled down. So like this, it keeps on happening. And after some time, we are going to get a shape like this. So this is what is called the jet binder jetting. That means we have a binder which comes out from in the form of a jet from this printer head. So this is one technology. Next, we can join the powder, which we have shown that this powder can be joined together with help of a glue. That means adhesive. Here, in this slide, we are telling that the powder itself can be joined not only with help of glue, but they can be heated and they can be fused. So what are the methods with help of which this can be done? The first method we call as like thermally fused selective heat sintering. Thermally fused, that means we are using some heat, and with that heat, the powder material will be fusing together. And this joining together is generally called as sintering. So we would be sintering the material. That means sintering in what manner? Say I have got a tray and I spread the tray with powder like this. The entire tray is spread with powder and I heat the entire tray. Then the entire powder is going to solidify. But I do not want the shape like this. I want that the powder should solidify in this particular manner only in the form of an L. I want the powder to solidify in this manner. If I want the powder to solidify in this manner, then I have to ascertain that the powder of this vicinity are only getting heated up. The rest of the powder are not going to get heated up. And that is how these powder are only going to melt or they are going to sinter together. This is one way out. How am I going to heat it? Maybe I have to use a heat source. What can be that heat source? That heat source can be laser. That heat source can be laser. So if I'm using the heat source as a laser, then I can add one more term into it and I can say that laser sintering. Instead of using the word what we call as heat sintering, I can call it laser sintering. But again, the same question comes, do I need to sinter the entire material? No, I do not want it the entire material. I want that the laser should fall on a particular area only and that area is only going to sinter. So I will be calling the name as selective laser sintering. I do not want to sinter the entire area. I want to sinter it only a particular part of that area. So the name is now SLS, this one, selective laser sintering. In a similar fashion, we can use electron beam also. Only thing is that the selective laser sintering can be carried out in open atmosphere, but in case of electron beam, we have to use a vacuum chamber. There is a good point, bad point, both move with it. A vacuum chamber means you will be in a position, or I will be in a position to handle materials which are very susceptible to oxidation. So it can be handled there. But the drawback is what? That you have to have a vacuum chamber. And the product that you are creating in the vacuum chamber is again a constraint. Constraint means what? Like it will depend upon the size of the vacuum chamber. So this is it. Next is what? Multi-jet fusion melting. Multi-jet fusion melting. Now, this is a process where you are using jet, you are using adhesive, and you are using melting as well, fusion as well. So this process will be utilizing all the three together. Now, to give a more a schematic input to you, we will be taking up what we call as selective laser sintering slightly more detailed format in the next slide so that you can visualize what is happening. Now, this is what it is called as selective laser sintering. What is there in this method? Similar to the method that we had earlier seen, where we had used a laser head. This is the laser head which is going to give you the laser beams. Now, again, we are having powder. The powder can be kept only in one chamber or in two chambers, maybe. Like if you want it to be symmetrically added, two chambers are better than one. So the RAM of this chamber is going to move up in this particular manner, and when it moves up in this particular manner, then there will be a roller from this side. There can be roller similarly from other side. So the roller skims and drops it here. The powder is dropped here, and again the laser beam is moving selectively over this material, this powder material, and slowly it is getting sintered due to this laser heat. And as a layer gets sintered, we pull it down. Again, another layer of powder is placed, and like that, slowly we are going to get the shape that is shown in this blue color. The blue color shape that is being shown, that is the actual material which is forming. So this is the example of what we call as selective laser sintering. In a similar manner, we can use electron beam welding also, but only thing is that the electron beam welding has to be carried out in a vacuum chamber. Now, we'll give an illustration of what we call as multi-jet fusion process. Now, this is what is multi-jet fusion process. What is happening here? See, here what we are doing, we are having powders. These are the powder. Now, there can be two way out here in this case. The powders themselves, they are coated. The powders are coated, very difficult to write with mouse. So these are coated powders. So I can have coated powders. And once I have got coated powder, I can allow it to stand. So due to adhesive forces, the powders can stick together. Alright, this is one way out. Next thing is that along with this adhesive, one can add a little bit more of what we call as binders onto this. That will like increase the adhesion of the powder. Done. So how can this be like added? Again, with help of jet, you can add this. So these what we see here, these are coming from the jets, adhesives. So the adhesives are mixing up over here. Finally, to give more strength, what we can do, we can use some energy. We can use some heat energy, or we can use light energy. That means what we are doing here, we are getting into a curing process. That is CURING, curing process. So I can take adhesive coated particles, I can add adhesives to it, and then what I am going to do, I am going to use some energy. This energy can be heat. This can be heat energy, or this can be light energy. How light energy can join? Well, light energy is added so that there will be a chemical reaction in presence of light, and due to that chemical reaction, bonding is going to take place. So we have now a process where we are using multi-jet from here onto this particles, and then with help of either heat energy or light energy, we are going to sinter them, and that is how we are going to get this fused block like this. So this is the classic example of what we call as multi-jet fusion process. Next, we will be seeing the application of what we call as electron beam. So what is happening in electron beam? Well, this is the schematic of electron beam. What we are doing here, it is very much similar to what we do in case of brazing. If you people have seen brazing properly, then in brazing also we do similar thing. Only thing is that it is done in a very in a more crude fashion, brazing. What we do in brazing, we take a brazed wire. We take a brazed wire, or we call as brazed rod. We call it brazed rod. Brazed rod. That means a rod made up of bronze, different combination of bronze. So we will be taking two mating surfaces, and we will be keeping that rod in between, and then we take a gun, oxyacetylene flame we take, and with that blow gun, we will be giving heat to it, and the brazed metal or brazed rod that melts and fills into the cavity, and it solidifies and holds the two parts together. That is called brazing operation. Similar operation can be done here also, but instead of using what we call as oxyacetylene fuel source of flame, we will be using a very precise and minute electron beam. This precise and minute electron beam is going to fall onto a wire. Definitely, the like diameter of the wire will be very, very less. It will be in like what we call as micron level, very, very thin. And also, it is important that the heat is going to fall onto this wire, and the diameter of the electron beam that is going to form, that should be even less than this wire, so that the this beam can land up onto a particular portion of the wire and can melt it in a very controlled manner. So we have to have a wire of very like small diameter, and the beam which is melting it has to be of diameter even lesser than that. So if these are happening, then definitely we are going to like melt and remelt, and again melt, again remelt, and that is how we are going to generate a 3D surface with thickness. And this wire plus this electron beam, and this will be calling as gun in that case. This is easy to be maneuvered. That means it can be moved like this, it can move like this. That for that only we have shown an axis there, all possible directions, X, Y, Z, in all possible directions. This head is going to move, and the electron beam is going to melt the material directly without getting into a powder form. That is why this method is sometimes called as direct energy deposition. That means you are using the energy directly, melting the material and depositing. Now, in the next slide, I am going to show you again a comparison, like where a similar thing can be done. Here we are using a wire. In another case, we can use powder also. Let us see how it can be done. Yeah, here we are saying that we are using a laser beam. This is the laser beam. This is the laser beam, and this is a nozzle. Through the nozzle, powder is being fed into the nozzle, and the powder is being fed in such a manner that the powder from here and here, they are concentrating onto the laser beam, and the moment it is coming onto the laser beam, it is instantly melting and it is falling. And if it is moving up and down, then we are going to generate a shape like this. So both of these will be called as direct energy deposition. That means energy, with the help of energy, this either you take it in the form of a wire or you take it in the form of a powder. They can be directly deposited onto the substrate, or without substrate, it can start from scratch, and layer by layer, by proper maneuvering the head, you can generate very nice complicated shapes. If you are doing it with this electron beam, then definitely you can do it in an inert atmosphere, away from the oxidation troubles that we find. So these are some of the techniques which we are utilizing in what we popularly call as additive manufacturing. So we have the name as additive manufacturing, ADDI, additive. You might be laughing at the way I write additive manufacturing. There is another name to it, what we call as a rapid prototyping, or we call it display. We can write it as RP, rapid prototyping. Now, these rapid prototyping techniques, why rapid prototyping? It is because prototyping means we are going to make a prototype of the actual product, and this prototype can be generated very rapidly because from the very designing to the finished product, everything can be carried out through help of a computer and will be carried out very fast. That is why the name rapid is given, rapid and then prototyping. Mostly we are dealing with non-metals here in this type of processes. Now, having gained knowledge about the basics of manufacturing from the prehistoric age to the modern age, that means we have come across from the conventional manufacturing, where we are mostly using subtractive methods, to the latest one where we are using additive manufacturing. We are adding layer by layers. Now, we have done all these things. We have gained so much of knowledge. Where are we going to use these knowledges? Now we are going to see that how these type of knowledge or technology that we have gained can be utilized for the biomedical applications. Let us see. Well, this is a slide which is showing us what we call as 3D printing for biomedical application. Again, I'll come to this word as 3D printing. 3D printing means what? Like, since we are into this additive manufacturing, and the additive manufacturing is doing what? It is like manufacturing things layer by layer, as if whatever we are seeing here is getting printed. That means if I want to print this slide that we are seeing here, what we would do, like we'll be switching it to the printer, we'll give a command, and the ink that is stored in the printer cartridge, that will be sprayed over the white paper in such a manner that wherever there is a dark one, there will be a line there. Similarly, we are going to get the entire thing that has been sketched here replicated onto the paper. This is called 2D printing. We are going to get everything in a 2D. How about getting something which would be slightly elevated? That means one layer after another thing is going to happen. And then we are going to get the real product. Whatever we get in real product, like we know that we give 3 dimensions to it. So length can be drawn on the paper, but they have to give a height to it. So it becomes 3D. 3D printing has to be done. Now in this slide, we are going to talk about the 3D printing for biomedical applications. And here we find a very important term written here, bio-ink selection. That means we are trying to draw analogy of a modern technology with some existing ones. See, when we are printing something on a piece of paper, then we say that we have to use ink to write, we have to use ink to print. Now, by this time, we know very well that the ink that we use to write on a piece of paper with a pen is different than the ink that is used to print with a printer. But still, we try to draw an analogy between the ink of a pen and ink of a printer. In a similar fashion, if we are going to devise something for biomedical application, we will be using something which will be similar to the ink that is we are using in a pen, but here we will be using the term called bio ink to ascertain that whatever we are going to print and make is for biological application. Now, what are the techniques that are used here? First of all, we'll be talking about this bio ink. What is this? This is basically a polymer. Bio ink basically is a polymer. And within this polymer, we can add either we can add medicines, we can add live tissues, which will be seeing later, as which will be called as tissue engineering. And the polymer that we are having here, that initially is in a very fluid state. But if we want to give some shape to it, regular shape to it, this fluidity has to be arrested, it has to be lost, and it has to have some fixed dimension. So that will be accomplished with help of this cross-linking process. So now we have got bio ink, we have got this cross-linking process, and along with this bio ink, we can add these cells, that is living cells can be added onto it. So we are in a position now to use this bio ink. Definitely this bio ink is one which is biocompatible to the place where it is being used, whether it is animals or human, it has to be biocompatible. It should not be toxic. That is one constraint. So this is what is the biomaterial and how it is going to be utilized. We have shown three processes. We can use extrusion-based process. We can use inkjet type of process where the ink will be dropping onto a particular surface and then it is going to get cured. Or we will be using some laser-assisted bioprinting. Again, the similar thing will be happening due to the laser. These are going to fuse and then it's going to melt and solidify. After melting, again, it is going to solidify. This is how these shapes are going to generate. What are the applications of this type of bioengineering product or biomedical product? Drug screening. You can use some material. We can use the carriers made up of this bio ink, and then into these carriers we are going to inject the like drug, and we can transport these drugs made in this particular manner directly into the place where it is needed. Now what happens, like if you are having headache or you are having ache in your toe of your feet, what we do, we swallow paracetamol, it goes into our tummy, the liver will be spinning at least half of the foreign chemical that has come, and then it gets absorbed in the blood, and then the blood carries it to either toe or head, irrespective of its requirement, it will be passing to the entire body. So even if you are having headache or you are having a toothache or toe ache, you swallow one paracetamol, all things pain will be going because it has been equally carried throughout your entire body. But what if I do not want to destroy or disturb the entire the entire system of the body, but I want that it has to be delivered at one particular position only, then it has to be carried out. It has to be carried out in a particular manner, and for that we have to use this biomaterial. It has to be shaped into a particular format. I'll again give you a small example. Like some of you or some of us might be taking what we call as probiotics. Probiotics are some of the biotics which contain these bacteria, and they are encapsulated in the capsules, and these capsules are made in such a manner that they will be passing the like HCl content of our stomach, and they will go directly into our intestine and then deliver there. So the coating is made in that particular manner that they can withstand this HCl content in our stomach and pass on from the stomach into the intestine where they are going to deliver it. So these are some of the applications of this biomedical 3D printing. I'll show you another slide, which is a more simplified slide, and you will be able to grasp things better in that. See, in this what we have done, we have taken a biomaterial and we have added some living cells into it. This can be living cells, this can be drugs, anything can be done. But then what we are using these three popular techniques, that is inkjet based, extrusion based, and light based. And then we are going to shape it, and then this will be delivered. So this is one way out. Next thing is that, as I had been talking, that we will be using the live cells. So when we are using these live cells, that means tissues, we are going into the what we call as tissue culture directly. Say for instance, I have to manufacture an organ, human organ. So definitely I have to use the live cells. But how am I going to bind them together? I have to use a biomaterial. And if I have to give it a particular shape, then again, what I have to use? I have to use an RP process. All right, let me see. Let us see how we are going to use that. See, this is the slide where we want to manufacture this organ. What is this? Let us say we want to manufacture a heart. Heart is to be manufactured. So what we are going to do now? We take this heart and then we will be creating a 3D profile of that heart. How can that be done? This can be done optically, this can be done with help of MRI, this can be help of CT scan, computer tomography, magnetic resonance, mapping, and only a optical thing. Sorry. So we convert this into what we call as a 3D CAD model. With help of this 3D imaging, we grab it, we grab all the dimensions. Now, once all the dimensions of the human heart is known, then I can generate a similar thing in a 3D CAD model. So I have a CAD model. Maybe there are many tools. I will be talking about those things in the next slides. So with help of those softwares, I can generate a 3D heart. And then this is to be machined. And those of you who have taken up courses in CAD/CAM, you know that in order to move the machine, the CAM machine in a particular manner, we have to have the applications and utility of G codes. So these dimensions would be converted into G codes, or you can say that G codes will be utilized to move the head across. And then once this is done, we come to this particular machine, which we call as RP machine, where you see these human cells and this bio ink are mixed together, and they will be deposited over this plate, and slowly this will grow up in this manner, step by step. Finally, we are going to get a heart, and that is, this heart will be a scaffold type of heart. Means we will be getting a scaffold, and into that scaffold, the human tissues are going to grow of its own. So this is the level of research we have gone into, right from the Stone Age, where people used to make things out of stone. Now we are in a position where human is thinking of developing a heart from scratch. I will be giving another slide to you to show that not only can an entire heart be repaired, that will be a very big thing to do at the moment, but definitely we can think of the shorter things or the smaller things like components of heart. Like if I need to make this particular valve for a particular portion, not the entire heart, but this valve, if it is metallic or in nature, then there is a tendency of the body to reject it. Even if I am using some a material which is made up of any human thing only or animal product only, but there is again a tendency of the human body to reject that, because my body has got a definite entity than the other person's body. So whenever I'm transplanting something, like I've borrowed something from maybe that's a human part, but when the moment I put it inside my body, the body starts rejecting it. That is the reason why, like all those patients who are into kidney transplants, they have to maintain a very strict and disciplined life, because the body tries to reject that. It has to be made to understand, to accept it. But the same kidney, if it would have been generated by my own body cells, then this rejection rate would be there and be widely accepted. So the entire technology of this tissue generation by bioprinting is in this direction, that whoever needs a part, implant, the technology is going to utilize his own body cells and manufacture the part for him so that it can be implanted in his body so that the body does not reject. This is the the ethos of tissue engineering by bioprinting, which can be utilized for human. The next part of it is what we call as drug delivery with tablets. I have talked about this a little bit earlier, but this is another important area where this like bio material and this the rapid prototyping would be very much like utilized. So what we are going to do, we are going to devise very small things with help of this 3D printing. Small device has been made, and then the small device will be soaked in the medicine. It is going to absorb the medicine, and once it has absorbed the medicine, it can be delivered directly onto that part. A practical application of this drug delivery with tablets, or the better form of it, without tablet, also drug can be delivered onto our body. And wonderfully, this can be done. You know how, like, say for instance, I am having a pain, too much of pain. What I do, like, I swallow a tablet, paracetamol. It goes into my tummy, and then again it does all those things. Then only I will find that the pain in my hand has relieved a little bit. So, in order to relieve the pain of my arm, which I am having at the left arm top, I have swallowed a tablet that has gone into the stomach. What is like, engineers never think it like this. Doctors may think, but engineer will be thinking that let me attack the area where the trouble is. So if I'm having pain in my hand, why should I put the drug in my stomach? Let me put the drug directly in my hand. So what am I going to do? I have to devise a mechanism where the drug can be delivered directly into my hand. Now, what I can do, I can put an injection there. That is the best thing possible. Now, putting an injection is definitely a thing. But nowadays, we have developed a better form of injection, what we call as transdermal drug delivery system. Transdermal drug delivery system. That is what we are going to see now. See, this is what is called this white portion that we see here. This is what is called a transdermal drug delivery system. Here we are having small micro needles. Small micro needles are made on this paper sort of thing that we are seeing, and this will be stuck on our skin. From there, the drug is going to go inside our body. Now, there are two aspects of it. First aspect is that there are different types of needles which can be like manufactured on this adhesive tape. So what are the different types of manufacturing techniques that can be utilized here? Again, you can see here. These will be like inkjet type of inkjet 2D, 3D printing. That is one way out. The other one is stereolithography. The third way is like fused deposition modeling. So stereolithography, 2D, 3D printing, and fused deposition modeling, that is popularly called as FDM. So since we did not talk about FDM earlier, let me talk about FDM. The FDM is a principle which is very much similar to what we had seen earlier, that is direct material deposition, DMD, and FDM. They will be working in a similar method. In DMD, what we had done, we had allowed the energy to be incident on to the rod directly, and it has melted the rod. And if you are melting it, if you are moving the rod in a particular fashion, you are going to get the molten things also lying on that particular orientation. FDM is also in similar fashion. Only thing is that here it is not a metallic rod, but it's a plastic rod, polymer rather, to be using a very layman's language, polymer. And there are these are electrically heated. electrical resistance heating would be there. So the wire polymer would be softened and it will become viscous, and then it will be laid in a particular manner where it resolidifies and becomes firm again. So that is what is FDM technique. And then we have got this 2D and 3D printing. Here what we are doing, we are using either a bio ink, which is in liquid state, or we will be using powders, solid powders, but we will be using a thermal energy as is being shown here. We can use a thermal energy here to melt that, and then there will be like some sensors which will be allowing it in a controlled manner. Similarly, we can have some piezoelectric actuators here. Piezoelectric switches will be there, which will be actuating in a controlled manner with electrical pulses, with the help of which the material can be forming in fall in form of drops. So that is how very small needles can be made. These are called micro needles. Now these micro needles will be stuck onto the human surface. Let us see how it is done in the next slide. Now here we have got a schematic. Here we are showing transdermal drug delivery. That means the drug will be delivered through the skin. There are three methods. One is that we will be having a solid microneedle. That means the microneedle will be a solid one. Next, it is a coated microneedle. Next one is consumable microneedle, another is hollow microneedle. All these four have got four applications. Let us talk about the first application where we are using a solid microneedle. Where the microneedle is working, you see there are like three layers shown here. This is the dermis layer, that is the inner skin, dermis, and then on top of that there is an epidermis. And on top of that, we have this stratum, that is the brown colored thing that we see on the top. That is the topmost layer. So I take a solid microneedle, and with help of this microneedle, I am piercing it. I am piercing it in a manner that the microneedle touches this dermis. That means the skin it has done, where there is ample flow of blood vessels would be there. There will be ample number of blood vessels. Idea is that the drug will be delivered onto this dermis, and since there are so many blood vessels over there, immediately it is going to get transferred. Sometimes when we get hurt, you will find that only a very small peel of the top skin has come out, and we don't see any blood. Nothing is there. That means the skin, the top skin, the stratum, that is not having direct connectivity with blood. But if the cut is deep, goes inside, then we find that blood comes out. That means the dermis has got hurt. Okay. So we will be trying to allow the microneedle to go and pierce this dermis in all the four cases. But thing is that in the first case, once the dermis has been punctured, or the epidermis and the top thing has been punctured, immediately this microneedle will be removed. It will be removed, and in its place we are going to put some medicine. See, the medicine has been put here. So the micro holes that are being created, through those what the medicine is going to come into the dermis. The next one is what? The coated microneedles. Coated microneedles, like you pierce it, then the medicine that is present within the needles, that will come in contact with this like microneedles, of this dermis, and medicine is going to get into the bloodstream. After some time, when we understand that the entire medicine has been soaked into the dermis, this can be taken out. So in both these cases, both of them are taken out. The third one is slightly different. In the third one, what is happening? We are using a consumable type of microneedle. The consumable microneedle, when inserted, it is made up of total like medicine. Slowly and slowly, it will be dissolving into our system, and only the top portion is left out, which can be removed. Lastly, we have a system where the microneedles are hollow in nature. So you pierce it And once it has been pierced, then you put the medicine from top. So the medicine will be transferred directly into the system from top. So this thing can be used time and again. Like when we are giving a saline to a person in hospital, what they do, they take a needle, they put it inside our vein, and they keep it intact. So every time they are not putting the saline directly onto our veins, but they will be using that stopper over there and they will be putting it there. So similar things will be done here, but with help of micro needles. So the drug delivery system would be best in this case, the last case, and the other two cases, like first one will be least, because the moment you take this microneedle out, because of self-healing, many a times it happens that the micro holes that are created onto the stratum, that gets filled up very quickly. And the other things are also there. All are having their pros and cons. Manufacturing process, cost, everything has to be taken into consideration. But this is an example by which help of which the material will be transferred onto our system. Okay. Next thing is into the healthcare system. We will be dealing with healthcare system only. Next thing is the application of this into our surgical tools. So with the help of different type of surgical tools, we would be in a position to manufacture, with help of different types of rapid prototyping processes, we are in a position nowadays to manufacture surgical tools specific to the need of a person, very specific to the need of a person. Say for instance, like if you go for a tooth extraction, you will find that the surgeon is trying to take some fixed tools, and the tools themselves they hurt, because like the size of my tooth may be very small, and the material or the tool that he is having is larger than the gap in my tooth, so it gives me immense pain. So if we can have very specific tools made for my purpose with help of these RP processes, then things will be very, very easy and quick. So this I have given you an overview of how the manufacturing has moved from like the Stone Age to the ultra modern age, where not only we have discussed how huge things can be made, but also how miniature things can be made with help of RPs. Now, since many of the faculties would be there in this talk and researchers would be there, I will give you an overview or information rather related to some sources of this bioprinting which are open in nature. See, like we should be doing away from the use of what we call as pirated softwares. So I often tell my students that let us be honest enough. If I don't have money to purchase a genuine software or a proprietary software, let us not purchase that. But let us use some open source tools so that we are in the safer side. Maybe those are not very handy in nature, but definitely we are keeping ourselves safe. So with this motto, the last few slides, I will be showing you, or I will be giving you some information about the open source tools for 3D bioprinting. I have given the first two sources, that is the RepRap and TurboSquid. These are websites one can always refer to. Plenty of informations are there. RepRap stands for in short, it is standing for your rapid prototyping, replicating rapid prototyping. That is what is RepRap. REP, replicating rapid prototyping, and it is accessible to small communities. Anyone can utilize these things in developing world, like the developing world like India. No, we don't have so much of money to purchase the proprietary certificates and proprietary softwares. So we can use this. We can use the free softwares that are available in these RepRap sites and TurboSquid sites. These are all open source license under GNU, General Public License. So there is no harm. Anyone can use them. You can frame the machines also. The next things are NIH 3D print exchange and this Thingiverse. These both of them are open source, huge online database are there for 3D models. And the NIH is especially for the medical applications. Medical applicable models are there. If one is interested, one can go into this. They can see the models. They can develop things of their own. Next, I'll just give a small photograph to you about this. This type of machines can be made in very cheap manner with help of those websites. Lot of information would be there. So you can utilize those informations. You can buy these motors, etc. They are very cheaply available, and you can develop a machine of your own at a very bare minimal costs. I will also give you some more information about the softwares. All these softwares that I have jotted down here, all of them are free softwares, open source softwares. These softwares are the slicing softwares. What is the utility of slicing software? It is because, like in rapid prototyping, we generate a 3D model, and once the 3D model is generated, then we have to slice that model into small two-dimensional sheet-like things, and then each of these sheets would be taken up by the CAD model, and then the things would be again joined back to the 3D model. So to divide a 3D model into small slices, we use all these slicer, Cura, repeater. These are the softwares available free of cost. So anyone can utilize them to suit to their requirement. So that's it. I tried to give you information regarding the history of manufacturing. From there, we had moved on to the different types of like conventional manufacturing, and very specific about the 3D manufacturing and special like application in the medical. And also I've given you information about the free softwares that you can use for your purpose. That's it. Thank you for giving me an opportunity so that I could speak to you people. I know there are many learned people in the audience. So I have tried my best to give you information so that it can be helpful to you. It's not necessary that like this will be attractive to all people, but there might be few who would be interested in these areas, and there are many I know who already know this. For them this might have been a repeated session, but anyway, that will be always there in a big audience. Thank you.
Thank you, sir. Thank you, Vidyut sir, for giving us such a wonderful knowledge about ancient manufacturing to the recent one, 3D bioprinting, and many more in the area you have covered, sir. It was very informative, and I hope uh, all the participants must have enriched their knowledge. Anyone having a question can put their question to sir. One by one, we will take the question. So please raise your hand if anybody wants to ask question. Yeah, Dr. Ashok Kumar, please ask your question, sir.
Hello.
Yes,
Yes,
sir.
Yes, sir.
Hello.
Yes, please, I am listening.
You are listening, please.
Yes, sir. Do you have CAD knowledge for using 3D printer?
I mean, his question
Hello,
is, sir,
sir.
should we have?
Do you have?
Should we have the knowledge of CAD for
Yes,
using
yes.
3D printing?
Yeah, definitely. You have to have the basic knowledge of CAD programming. Has to be there. That is what, like I had shown you, the G codes are necessary. So one has to have the basic knowledge. But that is not a very difficult thing to be done.
Okay. So his question is such there's a deep knowledge is required, or just to know G code?
It depends upon the complexity of the material that you are going to design. If it is a very simple thing, then you do not require so much of knowledge. But if it is highly complex, like an object which has got lot of dimensional tolerances, and too many radius here and there, then definitely you have to have a good control over the geometry. Until unless you are having control over the geometry, you will not be able to replicate that in your 3D model.
Okay, thank you, sir.
Thank you.
Anybody else want to ask question to sir? Mr. Abdul Hussain, you wanted to ask some question? Sona Kumari. Yes, Sona madam, you can ask question to sir.
Hello.
Yeah.
Yeah, madam, please.
Hello.
Yeah, you can ask your question. We are listening you.
Hello. Can you listen my voice?
Yes, please.
Yeah, we listen your voice.
Yes,
Please ask
sir,
your question.
Yes, sir. I have one question, sir. Which type of energy sources used recently in unconventional machining process, sir?
I did not understand. Image sources.
Energy sources means solar energy.
Energy source.
Yes,
Energy sources means energy source. I thought image is anyway. See, generally in non-conventional machining, we can use electron beam, we can use laser, we can use plasma. You can use electrical as well. Non-conventional machining means, you see, EDM is a non-conventional machining. We use electrical power there. Isn't it? And then there are other machining things as well. We can use plasma energy source, we can use electron beam energy source, we can use laser energy source. For 3D printing, definitely we are using, apart from plasma, we can use all of this. Okay. See, in FDM, fluidized deposition modeling, there we are using electrical energy. Similarly, for the direct metal deposition, we can use laser and electron beam. All right.
Can I use solar energy, sir? Can I use solar energy?
See, you can use any energy. We use energy for what purpose? We use energy to either sinter and melt. If you have whatever energy source you use, if it is sufficient enough to do this purpose, it can be used.
Okay, sir. Yes, sir. Thank you, sir.
Yes, welcome.
Okay. Anybody else want to put question? Okay, all the participants are requested to be stay with us. We will be having a validatory session right now. So in between, if you have any question, please raise your hand. If any kind of doubt, I could see anybody from physics, mathematics, anybody? Sona Kumari has raised the hand. Madam, please ask your question. Sona Kumari, madam. Yeah, Dhruv sir, you are also in the line. I have seen you. Sona Kumari, madam, please ask your question. Her mic is not.
Next person. Next person.
Next person, Dhruv sir.
Okay, Dr. Arvind, if people want, they can write to me directly later on.
Yeah.
No issues. So,
okay. Having any question, please you can write to sir. I will share sir's mail ID to everyone. And and always you can have your chat with sir regarding your research and regarding any kind of doubt regarding machining, manufacturing, and any other topic also can discuss. Now we move to the next session of our validatory. Before that, I will ask our principal sir to kindly introduce to kindly give a vote of thanks for the present session to our distinguished speaker, Dr. Vidyut sir. So, Principal sir, please.
Good morning to Professor Dr. Vidyut, our coordinators, Dr. Arvind, Dr. Jayaprakash, and other faculty members. I am happy that this 5-day webinar on manufacturing and automation completed successfully. And especially today's session by Dr. Vidyut on the manufacturing process. I think everybody has enjoyed quite good, and they got benefited through the different lectures. I was just looking at and pursuing the participation of the faculty members. Today I found that total attendance about 60. Yesterday also I found about 60. Someday it went down, but total registration was about 97 or 98. Dr. Arvind, have you kept the attendance participant-wise, registration-wise?
Yes, sir. We have taken the attendance, sir, like that.
So there are some faculty members or students. Actually, I was first day I was looking at. There are some research scholars or students also participate in this webinar.
Actually, they are the research scholars, sir. They are the research scholars. Yeah.
Research scholars.
So they have written like the students.
Yeah. 3,
So
4.
that we will modify.
That was negligible number.
Yeah.
So, is it true that there are some faculty members who have not joined at all?
There are one or two, sir, like that. But so in one or two way, they have joined. Most of them have joined. So
actually, what I was thinking that it may be that some faculty members are attending or registering for webinar or faculty development program for the sake of certificates, for the certificate only. So you please see that student faculty members who have not attended majority of the classes or sessions.
Yes, sir. So 80% attendance was mandatory, sir. Attendance.
So you don't issue a certificate to them.
Yes, sir. We'll take care, sir.
And I'm thankful that thankful to all the faculty members, resource persons who have given their time to share their experience and knowledge with our faculty members and faculty members who have joined from other institutes. I am also thankful to Dr. Arvind and Dr. Jayaprakash for taking initiative in successful conducting of this 5-day webinar. Thank you. Thank you very much.
Thank you, sir. So, yes, now we will move to the validity session. Sir, we have started our journey of faculty development program on manufacturing and automation from 28th of February 2022. And the journey of our FDP started with the talk of Dr. Naresh Rai. He delivered his talk on aluminum alloy-based metal matrix composite. He has given an updated research knowledge on metal matrix composite and advantages, its use. And we have what we have learned that there is ample opportunity for a new scholar, newcomer to start their research in metal matrix composite. As he talked that the uses of metal matrix composite, that most of the automotive parts are being replaced by this metal matrix composite and other fiber-based composite materials. Now, moving to the next one, we are very thankful to express our deep gratitude to Dr. Anand Rai sir for giving his time from his busy schedule and delivered a lecture on aluminum-based metal matrix composite to our faculty development program. Next, moving to the next session, we had a next session on application of robotics in manufacturing by Dr. J. Krishnaiah, Associate Professor in Triple IT Design and Manufacturing, Kurnool, which is in Andhra Pradesh. Dr. Krishnaiah has discussed uh, right from basic of robotics, arm movement, homogeneous transformation matrix, also to the recent development in automated vehicles. And he also made a clear discussed about the industry revolution like industry 1.0, 2.0, 3.0, 4.0, and made a clear distinction about all the changes, significant changes in all area of industry happened. So we are very thankful to him for that, giving such a wonderful knowledge about the industry, and also suggested to how to cope up with the industry to the curriculum by introducing some or few courses right from the beginning to our degree and diploma students. So we are very thankful to Dr. Krishnaiah sir for giving updated knowledge about robotics and updated research which is going on automated vehicles. So next session we had on advanced lightweight alloys for automotive and aerospace application. That was the distinguished speaker for the session was Dr. A.K. Chaubey, Anil Kumar Chaubey sir. He is a senior principal scientist at CSIR-IMMT Bhubaneswar. He has enriched our knowledge about knowledge and formation about our knowledge about the alloys and formation of new alloys. We are also very thankful to Dr. Chaubey sir for enriching us and has shown the way for the new researchers to how to develop a new alloy for various applications, application-based alloy, how we can develop. So we are very thankful to him for giving his time and enriching the knowledge of the faculties who are attending this 5 days of faculty development program. The next session we had on mechatronics for smart manufacturing and delivered by Dr. M. Chandrasekaran, Professor NERIST, Arunachal Pradesh. Sir has enriched our knowledge about PLC, use of big data in automation, and suggested about how to improve by adopting some extra courses apart from the curriculum to enrich the knowledge of our student to cope up with the industry. Since we are the era is of automation now, so from right from conventional to automation, and sir has given a lot of many ideas how to improve. And the last session, fifth session, we had on manufacturing from ancient statues to human implant, given by Dr. Vidyut sir. Sir has given ample knowledge about ancient that is sculpture age manufacturing to 3D printing and 3D bio printing, many more things knowledge sir has given us, and we are delighted to have this knowledge. We are very thankful to Dr. Vidyut sir for giving his time from his busy schedule and enriched our knowledge and given the lecture for our 5 days faculty development program on manufacturing and automation. With this, I thankful all my distinguished speakers, management, principal sir, HOD sir, for giving me an opportunity to coordinate such a program for our college, and I have tried to do it with. So I would like everyone, all the faculty members of our department who has actively participated in this to make it successful, especially Mr. Amrit sir and Priyaranjan sir has given a lot many times, day night we have worked together to make this event successful. So we are thankful to them. Other faculty members of other departments also have suggested us as helped us to make this program successful, and we are thankful to that. We have successfully conducted this 5 days faculty development program on manufacturing and automation. Any suggestions? Any participants can give the suggestion, please.
Dr. Arvind, I was looking for that some feedback from the participants.
Yeah, that's sorry.
Can
Yeah, there is some technical issues happen right now. We will be sending the feedback form to your mail IDs and questionnaire about this 5 days FTP to your email ID. Please answer the question and fill the feedback form. Based on that, we will process the certificate to you. So everyone, we will be sharing that feedback form to you, and accordingly, you please share your feedback and give the answer to your questions based on the sessions we have attended from last 5 days. Yes, sir.
That's okay, fine. Then
Any HOD wants to give feedback, please. You're welcome to give, sir. Any kind of feedback? Dr. Bidyut, sir, I will request you to kindly, yeah, Abhishek Kumar has raised the hand. Please, Abhishek, sir, please ask your question. So, mic is-
Yeah, yes, please.
Yes, sir. Abhishek, sir, you want to ask question?
I think people have left.
No, no, he is there. Okay, sir. Bidyut, sir, I will request you to kindly give your feedback or any of your experience about this FDP. Any suggestion you have to do for that, and please, sir.
No, overall it has been very nicely managed and arranged. Only I had a little bit problem to begin with because I am not very much used to in Teams because the internet connectivity here is not that fast. So we prefer to use Google Classroom and Google Meet because it requires lesser bandwidth compared to Teams. Teams needs more bandwidth. That is one of the issue why I use Google Meet. That's it. Or else everything is fine.
Yeah, in Google Meet, sir, we don't have a recording option. So
the recording option, if you are purchasing it, like you don't give recording option. I think if you like this is a licensed version of Teams you are using.
Team is we have license version, so we have a record of all the sessions. So we have to keep.
In case of Google Meet, they don't give recording if you are.
I don't think I don't.
When
I was using, sir, it was. Yeah. So we have to keep a record for our future reference, sir, and that will be there with our institute. So anybody, all the participants, anybody can wants that slide, sir. Sir, I'll request you to kindly share your slides, sir, with us, and we will share this to accordingly to our participants.
Okay, I'll mail you. All right. Thank you.
Amrit, sir, I have one request. The persons who are raising the question, please allow their mic, sir.
Okay, sir. I am allowing.
I request you please allow them. Jiptesh Panda, you want to ask question, please? Please put your question. Yeah, I have seen Jiptesh Kumar Panda. Please put your question. Kindly enable his mic, sir, please. Jiptesh, could you hear us?
He is not in meeting, sir.
He's not in team. Just now he has raised the question.
If I've got a meeting to attend. If we can finish the session, I'll request
yes,
you to.
sir. Yeah, I'll request all of you them. If you have any other question, please write it to the sir. Sir will definitely answer the questions. Thank you, sir. Thank you very much. Please, very much, sir. Thank you, Principal, sir, for giving opportunity. Thank you, sir. Thank you very much, sir. Sir, we should conclude the session, sir. Principal, sir.